questions about literally anything. Um, I remember when I was first learning about this kind of stuff, it was very easy to get lost in the weeds of the details. And sometimes it's just so confusing that you sort of like want the re-explanation for everything. So I feel like, we're now halfway through the course. You've seen a lot of the material now, and it might be a good time to just pause and think about which parts confuse you. And I just wanted to set some time for today where we could address some of those issues. So if there's anything, like literally anything, that you're a little bit iffy on or that you're curious to learn more about, feel free to drop it in the chat and we can do that. And the reason that I do this is because today's content is going to be it's going to be new, but I'm not going to cover as much of it because recurrent neural networks, they are a very simple modification away from regular neural networks. And there's not too much to say here. So again, like, this is all very, very challenging stuff, and don't feel bad if there's anything that confuses you. Um, and yeah, like anything at all, drop it in the chat. Feel free to DM it, and then we can talk about it as a group. And don't feel shy about doing this because chances are that if you have a question, somebody else has the exact same question. And they're just too afraid to ask. So. All right, so we've got some questions coming in. I think I'll just go through them one by one. And to prepare for this, I'll pull up some of the old slides so that we can talk about this in more detail. Thanks so much for asking the questions, though. Very nice. All right. And apart from like specific technical questions, even feel free to just ask, what the heck is a neural network if the intuition isn't there? I feel like when you're learning, it is super, super important to leave no stone unturned. So if there's anything that confuses you, even something where you know how the math works, but you feel like you're missing a piece of the intuition where, things just you don't grok it. You don't really have a good feel for why things are or how things work. This would also be a good question to ask. But okay, so let's just go through these questions one by one. These are really good questions. So the first one concerns neural networks. So I will pull this up from our second lesson. And the question is, for the neurons in a neural network, what are the parameters that go into the neuron again? So this is a good question. And let's just go through to the diagram of a neural network to perhaps explain this a little bit better. So remember that in a neural network, right, the whole idea is that we have some inputs. These inputs can be really any arbitrary numbers, but they represent the features, right? Because remember, in machine learning model, we're trying to take features and we want to stick them into a model. So you put it into a model. This is like, you can think of it as a function, and then you output a label, right? So in any given neuron, the inputs don't have to be the features, right? Only in the first layer, this first layer right here, are the inputs to these neurons the actual features. So this is like feature 1, feature 2, feature 3. And so as we saw the other day, where we have this data from previous layers, then you would get feature 1 in, feature 2 in, feature 3 in. And then remember how this neuron calculates its output. It sums over all the features and it multiplies it by their weights. So F1W1 plus F2W2 plus F3W3, and then plus a bias is equal to Z. And then the output, let's just call this A. A is equal to F of Z, where F is some activation function, right? So what comes into the neural network? This is a good question, because if this was in the first layer, if this neuron was in the first layer, then you would be getting some certain number of features in. Now, in this diagram here, these like couple of neurons are actually not exactly neurons. What they actually are, well, yeah, we can consider them neurons, but they don't actually do anything here. Because remember, when you pass something into a neural network, you get these values in, and this is not fully connected with anything. You're just getting an F1 in, an F2 and an F3 in. So I think a more appropriate way of wording this would be, this is F1, this is just F2, and this is just F3. And this is actually your first neuron that actually does any processing. So this neuron, for example, would get inputs from F1, F2, and F3. It would run this calculation that we wrote over here, and then it would output something. So what you can think of this as is just successively applying this operation here, where you take in whatever is coming into the neural network, into the neuron, you apply this math that we defined, and then you pass it on to the next layer. So then this would pass on some output A, and this A would go here, it would go here, it would go here, it would go here. These all get A, but of course A is then multiplied by different weights along these connections. So in the first layer, the inputs that come into the neuron, these are features, right? This is by definition. So we have feature 3 coming in here, feature 2 coming in here, and feature 1 coming in here. But this is only in the first layer. After the first layer, the neural network has transformed these inputs into something else, into this thing called A, and the next layer takes in all of these A's as input. So you can think of it as the neural network is trying to transform these numbers repeatedly into something that's more and more abstract until it can use this information to finally output the answer or whatever it is you're looking for. So, and the specific question was, what are the parameters that go into the neuron again? Well, I think it's very important here to disambiguate a couple of things. Activations, parameters, and hyperparameters. So remember that hyperparameters are things that users define. So hyperparameters are the things that are not learned by our learning algorithm. Remember we talked about gradient descent, where we're trying to use an algorithm to find the best weights possible. The learning algorithm does not tune the hyperparameters. These are things that the user has to define. So can someone give me an example of a hyperparameter in a neural network again, just to make sure that we're all on the same page?
Number of hidden layers.
Yeah. So that's one. Give me 1 second. So yeah, that's definitely one. Does anyone think? Can anyone think of any other ones other than hidden layers? So there's a suggestion in the chat that F1, F2, and F3 are hyperparameters. So remember that we discussed this earlier. So you're totally right that hyperparameters, these F1s, F2s, and F3s, these are the inputs. They're not defined, they're not learned by the learning algorithm, but they're also not something that the user can choose, right? I think there's a fundamental difference between the data that you feed the model and how you define the model. Hyperparameters concern the model itself. The model should be independent of the specific values of the inputs that are coming in. Of course, you might define the model in a way that is beneficial for the types of inputs that you give it. For example, remember yesterday we talked about how convolutional neural networks are designed with the idea in mind that images have these properties like translational invariance, spatial locality. these kinds of things. But in fact, these are not hyperparameters. The inputs are just the data. Can anyone think of any other things that we might change about this neural network other than how many of these hidden layers there are that humans must define that you cannot learn with a learning algorithm? Yeah, exactly, right? The number of units in different hidden layers. So in this layer, you could choose, in this case, to have 4. But of course, in other cases, you might choose that you want 100 of these hidden neurons in each layer. You might want 200 here, et cetera, et cetera, et cetera. This is an example of a hyperparameter. So this is an important distinction to make. You can't train your hyperparameters. They're not learned by the model. Okay, then you also have parameters. These parameters are the ones that are learned by your learning algorithm. And in this case, you simply have all of these weights as the parameters, right? These are the weights that are multiplied by all of these inputs on incoming edges that are summed up to make an activation. And then finally, an activation is something that is dependent on all of these other things, the parameters, the hyperparameters, and also the data. So the activation is defined as this thing, A. That's why we call it A. This is the activation. And the activation is the specific value that a neuron takes when you fed an input into the model. So suppose that you have 3 inputs, F1, F2, and F3. These specific inputs give you an activation of the value f of z, and z is defined as this. So this is the specific value that the neuron takes on. And as you can see, it depends on everything. It depends on these w's, which are your parameters. And notice that the number of w's in here depends on the number of hidden neurons that you have. So this depends on your hidden size, which is a hyperparameter. And of course, these f's are your data. So these activations depend on all 3 of these different things, your data, your parameters, and your hyperparameters. And they're basically just the specific values that come out of each neuron when you feed a specific input in there. So these are all very important distinctions to make. And so going back to the original question of, for the neurons in a neural network, what are the parameters that go into the neuron again? Well, this isn't really a well-defined question. So you have the parameters that go into the neuron. The parameters that are that are on the incoming edges to the neuron would be W1, W2, and W3. And these are the weights that are learned. So remember, parameters are weights that you learn. So that would be the more correct terminology to use. And then maybe the other thing that you might be asking is, what are the input values, or what are the activations that are coming into the model? If you were at the first layer, it would be features. If you are at any other layer, it would be activations. So you would have A1, A2, A3. If you were at a layer that wasn't the first layer, it wouldn't be the features. It would be the input activations. And these are simply the activations that came from the neural network's previous layers. Okay, so we talked about parameters, we talked about activations. And so these two are different things that we need to clarify to make sure that we're not confusing them. So, and you're totally right. Like, it might be a little bit abstract or difficult to think about what exactly these activations mean. But in most cases, you don't have to worry about this. You're just like, the neural network has learned that this activation leads to this activation, leads to this activation, that eventually gives us a good model. And That's pretty much all that we care about. And this is a theme that should hold that should generally hold true for the rest of this class, which is that I think mainly what you're really responsible for is to know how to apply these technologies. All of this theory that we're covering is just a sneak peek into the black box, and it's just a bonus. Like, you're in no way responsible for knowing this, but I feel like it's something that's really cool and that you already do have the requisite knowledge to understand. So that's why we're covering it, and we hope that you find it interesting. But hope that answers your question for the first one. The parameters are the weights that define how the incoming activations interact with the final value. And then that is not to be confused as with the values that are coming in, which are called activations that are multiplied by these parameters. All right, so we also have another question, which is, how did you do the math between the matrices yesterday? Was it just matrix multiplication? And also, how did you know that there were 4 biases, so it was 16 instead of 12? So this is also a really good question, like the last one, and I think it's worth clarifying. So let's talk about this. To answer the second part of the question was, how did you know that there were 4 biases? This is simply by definition of a neuron, right? Remember that our neuron takes in a set of values. Like, let's just say that there's this activation, this activation, this activation, bad arrow. You have A1, A2, and A3. Remember that, again, we defined the neuron's output activation A was equal to the activation function applied to A1W1 plus A2W2 plus A3W3, right? And what is it? Oh, wait, sorry, plus a bias. And so what does this mean? You have one neuron that has a bias and 3 weights. So 3 weights plus a bias. And how many of these neurons do you have? You have 1, 2, 3, 4. So if you have 4 times, and each weight and each bias should be just considered one parameter. So this is 4 params, 4p. So then 4 times 4 is 16. That's how you would know. So the question basically, how did you know there were 4 biases? Just by definition, right? Because we defined the neuron to be this function that does this, which has 3 weight parameters and 1 bias parameter. 3 plus 1 is 4, and then if you have 4 of these neurons, then 4 times 4 is 16. So that's how we know. And then the first question, how did you do the math between the matrices yesterday? Was it just matrix multiplication? Yeah, so it is. And I just mentioned this briefly in passing because I didn't want to bog everyone down with notation that they might not have seen before. But if you're curious, it turns out that basically what we were talking about earlier, where every neuron can be represented as some A1 plus W, so, whoops, A1 W1 plus A2 W2 dot 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 plus AN WN plus B, or if we just ignore the B right now, because we can just add it on later, this is actually what we call a linear combination of all of the input representations. And what happens when you take a bunch of linear combinations, not only for this neuron, which was what we just wrote out, but you do all linear combinations for all of these neurons. Like, you take this linear combination of these, then you take another linear combination of those, and then you take another one, and then you take another one. It turns out that you can represent this super nicely in matrix form, where all of your weights are just stacked in here. I don't quite, it like depends on how you write it out, or how, whether you put X on this side or X on this side. But basically you stack all of your weights here and you just got a bunch of W's. And then it turns out that when you multiply this with a vector x1, x2, x3, you will get out a vector a1, a2, a3, a4, which are precisely the activations that come out of this thing here. So this comes out a1, a2, a3, a4, like your input was x1, x2, x3. And just based on how the calculations work out, if you multiply this input, which is this, with this matrix right here, which is basically our huge weight matrix, then you get out 4 activations, which are these activations And this is just a much, much prettier way of saying the exact same thing. And of course, if you wanted to add the bias, then you would add some bias vector here, B1, B2, B3, B4. So don't worry too much about how this works, because perhaps we don't know how to do matrix multiplication yet. The key thing that you just should know is that there's a very pretty way of writing neural networks that uses matrices. And again, coming back to that original idea of black boxiness, don't worry too much about specific implementations. I think that just having an intuition, I think, is the most important thing. You should have an intuition for how neural networks work, right? It takes in an input, and there are all of these functions that lie inside the neural network, and it's just continually transforming this input into weirder and weirder and weirder representations. And eventually these representations can be sort of synthesized into an output, which is like, if you're doing classification, it would be an output between 0 and 1, where 0 is a dog and 1 is a cat. And as for what exactly these weird transformations are, you don't have to worry about it. All you have to know is that there are these mathematical operations happening that's converting an input to an output. And then, these operations at the very beginning, they're randomly initialized. They're not very good. So then we use an algorithm to make them smarter. And ultimately, most of the time, when you implement a lot of these technologies, all you are responsible for doing is to use the packages that other people have created, where other people have implemented all the math out, and all you have to do is call the model. And I think that in itself is a very, very important skill, because most of the time you won't be familiar with the cutting edge research in a specific area, but they will have written packages that can help you execute their ideas. So um, that's pretty much it. All right. So I hope this clarifies some of the ideas behind artificial neural networks. Does anyone have any other questions about literally anything? I know that yesterday was pretty long and difficult because we covered a lot of different new concepts, especially ones of features and convolutions and all these weird things. So if you have any other questions, I will give some people some time to leave them in the chat. And really take advantage of this time, because there are not many opportunities for us to like slow down and review different things. So if you have any questions, now is the time to ask them. Okay, so everyone's good on everything? Okay, cool. Well, I think at the very end, we can also reserve some additional time for questions in case you think of any, but we can get started with today's content, which is about recurrent neural nets. All right, so recurrent neural nets are a really cool thing. They are the next big class of neural network models that we will be looking at. And in fact, we only look at one more, which are transformers, I think tomorrow. So recurrent neural networks are very interesting. They have lots of very important applications. And as I mentioned, they fall into one of the big categories of neural nets. Of course, we have the MLP, which we've spent a lot of time talking about. CNNs, which we looked at yesterday, which are these things that can look at inputs from images and be like, there are these cool features that define certain characteristics of objects like cars, trucks, vans, bikes, and we can use these filters to extract them and learn these features and ultimately output a classification. And then finally, we have recurrent neural networks, which we'll be talking about today. There are a whole lot of very interesting applications of recurrent neural networks that you might have seen in real life or maybe not. There are these ways that you can use recurrent neural networks for computer vision tasks. Here, there's an application of this to, I think, classifying or at least segmenting this car out from the image. I'm not totally sure what's happening here, but that's one application. One that's super important is what we call load forecasting. This might help you better allocate resources. This has lots of applications in lots of areas. For example, if you think about electrical delivery, how we forecast the load from the grid, this can help us better allocate resources to deal with high load areas. You might think of load at airports or on highways, or in general for transportation. You might want to predict when there are going to be a lot of people traveling through a certain area, so that perhaps maybe you can increase security. You can um, or you can maybe block off other people from, or maybe you can find some better ways to regulate that traffic or whatever it may be. There are very interesting applications at the intersection of computer vision and NLP that use recurrent neural networks. One of them is image captioning. So you feed some neural network an image. In fact, this is a CNN. You feed it an image, it gets some features out, and then you use a recurrent neural network to take in these features, and it can generate a sentence that tells you what is happening in this image. So very cool. And finally, this might not be a problem that you've heard of before, but it is of central importance in biology. This is the protein folding problem. And the whole idea is that proteins do a lot. They do a heck of a lot in our bodies. They basically perform all of our cellular functions, almost all of them, and they play a central role in regulating a whole lot of different things about our body. And one of the big problems in biology is we don't really understand how these proteins fold in terms of what they look like geometrically, physically, after they fold on itself. And the problem is that these proteins that regulate maybe things like our immune response to certain diseases, they sometimes they go defective. They fold and they fold incorrectly, or perhaps um, drugs that we create, they do not dock with these proteins properly. And it's a big problem. It's a big open problem in biology to say, given a chain of amino acids that make up these proteins, how can we figure out how it's going to behave? And how can we design drugs that work with these proteins to fight disease, to do a whole lot of different interesting things? So RNNs are one of the techniques that people have seen great success with using in the protein folding problem. So as you can see, all of these different neural network architectures have a whole slew of different applications. We saw with ANNs, they're very good at handling sets of features. Um, CNNs are very good at analyzing data with local sort of spatial organization, like images. We didn't really talk about images, video and audio, but that what we might talk about a little bit today. And finally, RNNs have a whole lot of different applications in this area. And we'll talk about the common thing that all of these things share that make RNNs so effective at the task. Oh, and another thing is that RNNs are very popular in the NLP community, and we'll talk about why this is in a moment. All right, so we already talked about this a little bit, but RNNs are closely tied to artificial neural networks in some certain ways. Now, we already talked about this before, like you have some certain inputs, and then you multiply all these inputs by all these weights, and you get all of these neurons here, you get the activations out. And then you just keep doing this repeatedly and repeatedly until you get an output. So we talked about the training procedure. It's pretty simple. Like you initialize the weights randomly. You fetch a batch of data, you do a forward pass, you calculate the loss, and then you use gradient descent, you use backpropagation to make all these weights just a little bit better, and you do this like 1,000 times, and then your model becomes very good. So now we are faced with a problem. So the entire problem with these artificial neural networks, well, this is just one of them, and it's very problematic when you look at certain types of data, is that they don't handle sequential data very well. If you think about some of these problems that we've talked about, right? Load forecasting, it's a time series problem. You have a certain, you know, a certain set of observations that you make every hour, which is perhaps the load, and you want to forecast the load from that. Well, this is hard to do with neural networks, right? Because first of all, you might have hundreds of hours or maybe thousands, hundreds of thousands of hours of data, and if you feed this into a densely connected neural network, your computational complexity will blow up very, very quickly. And if you can imagine, if you have like a million or a billion inputs here, how many weights do you need to have? It's going to be a crazy amount, and it's not going to be good, because the more weights that you have, the more data you need to learn a good model, which is very difficult to come by. Data is very expensive. Um, Other problems like speech. There are a whole slew of problems with speech that we'll talk about tomorrow, and how we address them. But one of these is, again, speech is sequential, and it doesn't play well with regular neural networks. If you imagine just representing every word as a number, you might plug it in. The fox jumped over the lazy dog. But this is not great because sentences can be super long. You'll have an explosion with a number of weights, and there are different problems. For example, if you switch two words in a sentence, the meaning could totally change. But artificial neural networks are very, very sensitive to swaps in your position. Like, these specific features have to be pretty much constant through all runs. For example, if you had a sentence that was uh-oh if you had a sentence that was the the brown dog, right? The brown dog. This would be very, very different from plugging in something like the dog. Because in X2, this is the same neuron. In the first sentence, you have an adjective here, or you're describing the noun, but here you have the noun itself here. And this is going to produce big problems when you use a neural network, because the neural network has this implicit assumption that every single input is always generally of the same class. Like, remember when we talked about the iris flowers? X1 was always going to be, it was always going to be the petal length. Petal length. It was always going to be that. Like, you don't swap it. If you changed it to sepal length, your model would be completely bad. But in this case, when we add or we remove words, maybe we add adjectives or remove adjectives, the meaning of each neuron completely changes. And this is not good if we're thinking about language. So clearly there are some problems here that we need a better architecture to attack. And the solution here is recurrent neural networks. Now, recurrent neural networks have a couple of features that make them so good for the task at hand. First of all, they're designed to capture temporal dependence. Temporal just means time series. Um, and we will see why this is the case in a moment. They are what we call recursive, which means that we can apply them an infinite number of times to a bunch of inputs, and therefore you can have varied length inputs. So if you think about sentences, the dog ate, or the dog ate food, these are both valid sentences. But how would you put this into a neural network, right? If you had 4 inputs, the dog ate, what would you put for X4? You might put like a 0 value, but this doesn't really make a lot of sense. Or or uh or 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 yeah. And then if you had a super long sentence, a sentence that was longer than the number of inputs that you have. So imagine that you only had 4 inputs, but you had the quick brown fox jumped over the dog, then this would be bad, because then you have too many inputs for too few slots. So You can't do varied length with artificial neural networks. You can do this with recurrent neural networks. And then this final thing I will explain in a moment, but it allows for temporal indifference when needed. What this means is that when you're looking at time series data, right, you're looking at sentences or you're looking at load forecasting, there is a certain there are certain data points that are important to remember, right? For example, if you want to decipher the meaning of a word, a meaning of a sentence, when you look at the word food, you can't have forgotten that you have seen a verb and a noun, because then we know that the noun is applying the verb to this word food. The dog is eating the food. If you only looked at food and you ignored all of this, then you wouldn't really understand anything about the sentence, because in fact the sentence is about something eating something, whereas if you just looked at food, you would just know that the sentence is talking about food. So this is what I mean by temporal dependence. But sometimes if sentences become so long, or maybe this is more obvious when you talk about processing essays, or maybe um, like a blog, then of course like one blog post has nothing to do with the next one, or might have very little to do with the next one. So we need a system that can remember the important pieces of information and forget about the useless ones, because of course there's a cost to remembering things, and that's memory. You need to spend memory to remember something. And if it's not important, then you should not remember it. So all of these desired features of a neural network we want, and we will see how they're achieved using a recurrent neural network. So recurrent neural networks are a better idea for sequence data. That's the whole point of them, for sequence data. Now, how do they work? Well, this is the diagram of a recurrent neural network. It is quite simple, and it's actually quite nice. It's quite cool. So imagine that you have a bunch of inputs, right? Xt is the input at time t. You could have a bunch of different t's. So for example, x1, x2, x3, x4, x5. X1 could be um, the dog ate the bone or something. I don't know. And so these are all of your xt's. And what you want to do is you keep feeding it into this model. It'll do something, it'll spit something out, and then it'll send its state to itself in the next time step. So this might sound a little bit confusing, but let's unroll what we call unroll the recurrent neural network to understand what's going on. So this diagram here is actually equivalent to this diagram over here, where every input has its associated output and its associated state. And there's this connection here that passes the information from this state to the next state, and then to the next one, and then to the next one. So how does this work? Well, if you have an input, and we sort of talked about this earlier, maybe we have the dog ate blah, 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 blah. Then you would pass in the, which is x0, and it would be put into the state. This is like a state machine. What is a state machine? It is something that takes in some kind of input, and it looks at the input and it sort of deciphers what is important to keep in the state and what is important to delete. You can think of this as memory. So when you put an input into here, it updates its memory. It's like, okay, I see this word the, I see the stop word the, and it'll be like, okay, let me remember that. And then it'll spit something out. Now, this spitting something out could depend on what you're trying to do, right? There's a common application of recurrent neural networks in NLP, which is to take in a sentence and determine whether it's toxic or not. You can imagine that this might be very important in moderating things like Discord servers, maybe, or Twitch chats or YouTube comments. You want a model that can take in a sentence and be like whether this is a toxic statement or not. So then you would spit something out, and then this is a state, remember, it's memory. So we have to pass it on for the future. We can't just forget our memory. So then you pass on the state to the next time step. And then when you see the word dog, you will give that to your new state, and it'll do a synthesis of the old state and the new input that it's got. And it'll do what we call updating. Updating the state. This is sort of like learning something new and then registering in your memory without forgetting, without forgetting the past. So this is super important. You want to incorporate information, you want to update your state with new information, but at the same time, you do not want to forget the past. Now, we'll see how this is actually done using a neural network in a moment, but this is sort of the idea. You update your knowledge of whatever it is you're looking at. In this case, it's a sentence, and then you'll spit out another output. And then you'll just keep doing this again and again until you're finished. Now, you might notice that this is a very nice formulation because it doesn't matter how many inputs we have. We could have one, we could have two, we could have a million. It does not matter because every time we're simply taking in a new input and we're updating our knowledge, our memory of what's going on, and then we're passing it on to the next time step.
What are
So
we supposed to output?
yeah, so as I mentioned, this is supposed to, this depends on your task. So if you're trying to use recurrent neural networks for a classification task, then your h's, every ht would basically be a vector of like all of the probabilities. So if we were trying to do toxicity detection, then we would have two classes, right? We would have toxic, non-toxic. And so then your output would be just an array of two numbers. So then every time it would be like, oh, I think so far, I believe that the sentence is non-toxic. This would mean non-toxic because the second index corresponds to non-toxic. But maybe at ht plus 1, it saw a bad word, and then it suddenly thinks like, oh, 90% probability that it's a toxic statement, and then etc. So this would be a classification for classification tasks. You might also think about regression. Regression, an example of this would be load forecasting. So then ht would just be a number, like say, I expect, 500 cars to pass through this intersection, um, at hour 10 of the day or something like that. So you would output a continuous value on the real number line if you were doing regression. And of course, if you're doing classification, then you would output an array of probabilities based on the classification. Hope that answers the question. Any other questions about how these things work? Okay, great. So we have the general intuition now. We understand that you have a bunch of inputs. You're going to give it to your neural network, and the neural network is going to figure out a way to remember this information, store it in its memory, and then it's going to use its memory, its sort of understanding of what's going on, and it's going to output whatever you want it to output. So of course, in the case of classification, you will have an array of probabilities, and in the case of regression, you're going to have a continuous value. So what exactly is happening here? How do we do all of this stuff? Well, it's actually pretty simple. Now, just a couple of notational things. Don't be bogged down by all of these letters. Um, I will go through and explain what each of these means. And let's just start with H. Does anyone want to hazard a guess as to what H is based on what we talked about earlier? What do you think H would be? So remember that we talked about how there are these different components of a recurrent neural network. And what was the most important thing that I said multiple times about recurrence? Like once you feed something as an input into a model, what does it do? Anyone? So I think like, okay, so I'm starting to ask more questions because I really want to make sure that we're on the same page. If you don't know, do you want to just type in an IDK in the chat? I think that would help me understand where we are as a class. And if you know the answer, just spit it out. Okay, so the most important thing in a recurrent neuron is this idea of memorization, right? Remember we talked about passing in an input and it sort of commits it to its memory. It's like, I remember this about the input sequence, and every time you just keep updating that memory. So HT is actually the memory. This is just a number, a bunch of numbers that represents what the model has remembered about the entire sequence, right? So the model has represented its memory in this number ht, and let's see how ht is computed. So ht, the equation is right here. So don't worry about the g's right now. They're just other activation functions. Does anyone want to remind me what an example activation function is? It's the one that we did with the graph. Does anyone remember the name? From a couple of days ago. It's got a weird name. Yeah, exactly. It's called sigmoid. So these could be sigmoid functions. Sigmoid. Don't worry about these too much. They're just like there to add nonlinearities, because remember, if we don't add nonlinearities, the whole model just is a big linear model and it's not very useful to us. So apart from the sigmoid, we really want to focus on what is inside here. And so let's look at this. So you got sigmoid functions, and then you got a couple of things. You got wi xt, wr ht minus 1, and bh. So the first thing is that you might notice that there is an h of t here, and then an h of t minus 1 here. Does anyone want to make a guess as to what h of t minus 1 is, as opposed to h of t?
Oh, it's like the previous term.
Yeah, exactly. It's the previous thing that your model has remembered. So remember, at every time step, we update our memory. So then, of course, then whatever we had from the previous time step, we need to look at that, because you need to take in what you used to remember, and then you need to add in the new thing that you want to remember. So there's this weight value that determines how much to carry over old memories. This is super important. So imagine that WR is 0, right? Then this term goes to 0. And then HT will contain no signal from the previous state. And so that wouldn't be so good, or maybe it would be good, who knows. But then if WR was non-zero, then every time you would incorporate some signal from the previous state. If it was 0.1, then you would carry over 0.1 times whatever the value was. If it was 100, then you would maybe amplify the signal a lot. This weight, it just determines how much to carry over old memories. And then, of course, we have an x of t, which is the input here. And this tells us, and this wi tells us how much of the current input to commit to memory. So this basically defines how much of this new input do I want to remember going forward. And so then you will notice that when we combine these two, when we combine how much you want the current input to influence your memory, and also how much your old memory should influence the current memory, and then you simply add a bias term, then you get your new memory. So does that make sense? Hopefully this makes sense, where I think this is a very intuitive way of putting it. Like every time you want to memorize something, you have to tell yourself, I want to remember what I used to remember, and also I want to add in this new memory from my current observation. So
But
then, yeah,
so this h of t has memory about t at the time of t minus 1, but also t minus 2, t minus 3. Is that right?
yeah, exactly. And you can
Right.
see this by thinking about it recursively, because h of t minus 1 was actually dependent on t minus 2, and t minus 2 was dependent on t minus 3, and etc. So this is actually everything that you remembered, not just at time t minus 1, but also everything up to and including t minus 1 would be the correct way of saying it. So yeah, good question.
Thank you.
And then finally, for y of t is the output, right? Remember that when we talked about classification, okay, well, this is using different notation. This actually should all say y's. Y. And you'll see this in deep learning a lot. People use different notation for literally everything. But your classification would be this array of two values. So if you were trying to determine whether somebody was being toxic or not, then your y of t would sort of look like, maybe 0.9 probability that they're toxic, 0.1 probability that they're not. And how do we get this? Well, it's again quite simple. So this is your memory, right? This is like your understanding of what's happening in the sentence. And then you apply this, you multiply it by some scaling factor, a scaling factor that determines, how do you turn your memory into an output. Of course, you add a bias, and then you apply the sigmoid function, and that's what your output is. So quite simple, actually. You got a very intuitive sort of way of putting it. You got your inputs, you want to update your understanding of the situation, and then given your understanding of the situation, you want to create an output. And then you just keep doing this. You notice that these two equations govern the entire neural network. It's super, super simple. And you just keep applying this every single time you see a new input, and ultimately you will get, you'll build into your memory an understanding of the entire sentence, which is really, really powerful. And then you can, given your understanding, you can output some value. You can be like, this is toxic or non-toxic. So if this makes sense to everyone, I want to ask a quick concept question. What are the parameters of this model? And just as a reminder, the parameters are the things that you will be tuning through gradient descent. So we've got a very good suggestion in the chat, which is in fact correct. The WY, the WI, and the WR. That is exactly correct. And also, don't forget the biases, but they're not that important. So get the WI, the WR, and the WY. These three constitute the parameters of the model. This is really great. Good job. And the way that you can see this is that, well, you can do process of elimination, right? You just look at all of these symbols and you ask yourself, can any of these be parameters? So let's go through and maybe highlight some of these. Let's go to our highlighter. So if you look at YT, it doesn't really seem like this should be a parameter because it's the output of a function. This would be called an activation probably. So this would not be the parameter. H of t is the memory, but again, H of t is an activation, right? Because it's the output of doing some mathematical operation. You look at, so obviously H of t is not correct. H of t minus 1 is not correct either. And X of t, remember we talked about earlier, the input or the input activation is an activation. Like it's not something that you learn. It's neither a hyperparameter nor a parameter. So basically by process of elimination, and also of course your function can never be a parameter. Your function is always just there. You've defined it already. By process of elimination, we've sort of figured out that the only possible parameter choices are wi, wy, wr, bh, and by. And in fact, this would be correct because these are the parameters that define how much to carry over old memories, how much of the current input to commit to memory. And these are all variable based on the specific problem at hand. Sometimes you might want to forget things super quickly in certain problems, then you would make the WR super small and the WI super big, and then maybe vice versa in other applications. And then of course, the way that you turn your memories into outputs varies by problem, right? Because sometimes, you can just think of giving it a sentence and you can do a whole lot of different things. You can do toxicity classification, you can do sentiment analysis, you can even do machine translation. You can translate this toxic sentence into a different language if you want to. These are all different WYs that you will need because you need to learn different ways of converting your understanding of the situation to your output. So very, very good. Good job. It is indeed WY, WR, and WI. Those are the things that are learned through gradient descent. Nearly pretty much everything that you will see, at least in this course, for all models, the parameters will be learned using back prop. This is a universal truth in this course. In some other sort of maybe more interesting, newer parts of machine learning, we don't always use backprop to do updates to weights. But in this course, for purposes of this course, just remember that more often than not, your parameters will be learned using backpropagation and gradient descent. Great. Any questions about how this works?
No.
All right, great. Let's move on. So given this RNN architecture, there are a lot of different ways that we can apply it. So one specific way is you can do one-to-many, which if you think about all of the different applications here, this would be perhaps image captioning. Image captioning. What this means is you feed it one input. This would perhaps be the features of the image, and then you would put it through a recurrent neural network, and the neural network would try to caption the image. So if you gave it an image of a giraffe, it would maybe output the giraffe is there or something like that. So one-to-many means you feed it one input and it generates a bunch of different outputs. And your question at this point might be, well, didn't we say that we have to have a bunch of different inputs? Well, this is actually there's actually a little trick here that is not clarified on this slide here, which is that when you generate something from an input, say that this is an image of some giraffe. I'm an awful artist, so we'll just draw the giraffe like this. This is our giraffe. And you have an image of a giraffe here that's going in. It'll generate the, and then the will actually serve as the input to the next, and then this would predict giraffe, and then this would go into the next one, and it would predict is, and then it might go into the next one and predict there, or something like that. So we only had one input of a giraffe here, but then it generated implicitly using all this like stuff, it generated a bunch of outputs. So what we should actually be seeing here is these outputs are coming back into the inputs. So that's one thing. There's also a many to one scenario where perhaps this is exactly what we were talking about with toxicity classification. You would basically say, oh, what if you had a message that says, you're really cool? This is not a toxic statement by any of the stretch of the imagination, but you would feed the sentence into the model and you would take the last output, right? And if you think about it, this makes sense because if you took any of the earlier outputs, at this point, it's only seeing the word your. And at this point, it's only seeing the word really. Like your really could devolve into a very, very bad, mean statement, but you have to see the entire sentence to be able to make a classification. So we actually only in practice take the output at the last time step. So this would be many to one. Many to many is a very interesting thing because, for example, you might have machine translation. So you're really cool, and then it would put a representation in here that represents the entire sentence. Remember that these are the HTs, and they basically, the neural network has memorized all of these interesting things about the sentence, and then it can start generating a bunch of stuff. It can generate this in Spanish, in French. I don't know either of these two languages, so I don't know what it would look like, but it would start generating a bunch of characters or words in other languages, and this would be how Google Translate works. This actually is the old way of how Google Translate used to work. And then, of course, there might be many to many in this situation. It's sort of like a different thing where you don't wait until the last time step to start generating things. You start generating things immediately. So that's just another way of doing many to many. It'll be important for different types of technique, for different types of applications, but I won't talk about them in detail today. So these are the different ways that RNNs can be applied, and hopefully this makes sense. So this pretty much wraps up our technical discussion about RNNs. As a reminder, basically these are designed to handle time series data, time series data. This is the common thread through all of this entire lecture. They handle time series data. And you can apply them to a whole lot of different things. So if we look at the applications of RNNs, you can have language modeling and generation. This would be, for example, a chatbot. If you've ever gone on some company's website and they're like, yeah, chat with our virtual bot. Sometimes they'll be using AI techniques like text generation to speak with you, to do question answering, things like that. There's also a big application of temporal analysis and automatic speech recognition. This will actually be today's lab. There's, of course, lots of things with load forecasting, and it doesn't even have to be load forecasting. It's just forecasting in general. People have applied RNNs to analyze the stock market. Doesn't quite work so well, but it's an interesting idea. Of course, you can do electricity, load management. You can also look at traffic forecasting. You can do, and traffic doesn't have to just be physical. Like there's also internet traffic forecasting. If you think about the number of people, the sheer number of people that are on the internet right now, if you have this big event coming up, or maybe, like where millions of people are going to tune in into some server, you don't want them to crash the server just because of the sheer number of people that are trying to get data from it. So being able to forecast internet traffic can help people better prepare for these kinds of scenarios. And that could use RNNs perhaps. And also there's a computer vision. This is an interesting idea that we never really talked about. There's video classification, where you can use a CNN to extract features from all of the images, and then you can train an RNN to piece together every single frame of the image so that maybe you can do classification on this image, on this video, to be like, what are they doing? Are they playing a sport? Are they cooking? Or whatever it may be. And we also talked about image captioning. Captioning, where you feed in an image and you use an RNN to generate a sentence that describes what's happening inside this specific image. So There are a whole lot of different applications of RNNs that we will be exploring. That you can explore in your free time. But today, for our lab in particular, we will be looking at automatic speech recognition. So let's talk a little bit about this. Um, Automatic speech recognition is what you use when you do things like dictation on your Siri device, or when you talk to Amazon Alexa, you talk to your Google Assistant. They need to understand the speech that you're saying. So you speak a couple of words, it can understand you, it'll transfer it into text, and then it'll use some other NLP method to determine the best way to answer your question. So if you think about Siri, a lot of the technology that Siri perhaps initially was built upon, we talked about today, which I think is really cool. Um, so automatic speech recognition is kind of a tricky task, right? Because what you get from a microphone looks sort of like this. It's an audio form. It is some physical measurement of how the air that's coming out of your mouth interacts with the microphone, some physical measurement. And it looks like this. The problem is that when you just look at this audio form, there's not much you can tell from it. Um, there is it's just a big mishmash of different sort of artifacts of the the way that your the way that your mouth moves and produces sounds that sound like words. Um, so one interesting fact is that people have devised this thing called spectrograms, which provide a much better representation of speech than just the raw audio form. This is the physical measurement, and this one is transformed, transformed, transformed measurement. So the interesting thing about spectrograms is that they actually contain much more interesting information. And you might notice that it is given in units of hertz. So a spectrogram actually gives you the frequency information from a person's voice that when they're speaking. If you think about, maybe not speech, but if you think about a musical instrument, right? If you look at a piano, what does a piano sound like? Well, when you play a note, there's a certain frequency associated with that note, right? Maybe you play A, the tuning A. This is 440 hertz. This is the A that orchestra's tuned to. So then if you took like a physical measurement of a piano, it might look really dumb. Yeah, it might look like this, just like a big waveform. But if you put it into a spectrogram, or more generally, you put it into this machine called a Fourier transform, you would get a very cool result where here exactly at 440 hertz, you would get a big spike, a big spike. And then the function would be like 0 everywhere else. And this is a much more useful representation than this, right? You look at this and you're like, what the heck is going on? But you look at this graph and you know exactly that a 440 hertz note is being played by the piano, which is very cool. And it turns out that people can actually learn to read spectrograms. So obviously this might not mean anything to you right now, but there's actually a course at MIT that teaches you how to read spectrograms. So you take a physical measurement. No one could possibly dream of reading this. This is just a bunch of, confusing signals that are difficult to interpret. You take the Fourier transform of it and you get a spectrogram out. And there's a class that teaches you how to read this. I'm not sure what this is saying, but if you ask someone who took that course, they could tell you what this person is saying just by the spectrogram. And the importance of this whole idea of using a transform, is that when you have a signal, it has a lot of interesting information, right? Like this physical measurement contains all the information that you need in order to be able to decipher it. Because if you took this physical measurement and you put it in a speaker, you could hear it and then you could understand what was happening. So it's clearly got the information in there. However, it's not in a very good representation. It's very confusing. It's just a bunch of squiggly lines and people have a difficult time reading it. And when you put it through a transform, this is called a transform, or more specifically a Fourier transform. The whole idea of a transform is to take a signal, to represent it in a different way. To take a signal, keep all the information, but decipher it in a way that's a lot more manageable. You can think of this like trying to teach a kid. If you try to teach a kid how to do, um, if you try to teach someone a skill, it doesn't have to be a kid. If you try to teach someone a skill, it's sort of like the difference between teaching them in a really good way, where you're introducing all of the intuition and trying to make them understand, trying to make them really get a feel for what's happening, versus just throwing all the equations at them and being like, yeah, these are the equations that govern it. We don't really know what's happening, but you can figure it out. Um, so it's like the way that you communicate information that's super, super important. Or perhaps another analogy would be if you're trying to give a presentation to someone about some of the work that you're doing, the physical measurement is akin to giving a really crappy presentation that's really confusing and no one can understand, even though you have all the information there. You're explaining what you did with your project. They still have no clue because you represented it in a really bad way. But if you apply a transform, or in this case, a Fourier transform, you get something that's really organized. It sort of clears out all the clutter and it gets to the really key points, and it's much more easy to interpret. And it turns out that this is much, much better for neural networks to learn from. Neural networks very much like transformed measurements, because naturally it's a transformed measurement. It's much easier to understand, not only by humans, but also by computers, because otherwise the neural network would have to learn to do a Fourier transform, which I don't think would be very fun. So the whole idea behind automatic speech recognition is this pipeline, right? You take the physical measurement from your microphone. So the first step is to transform it into a spectrogram. And then you apply a bunch of different techniques. So there are a lot of different ways that people do speech recognition using neural networks. We'll just call it generally, it's called modeling. This sounds very vague because it very much is, but we won't get into the details today. The whole idea behind modeling is you take the spectrogram, and because the x-axis is time, you can basically apply a temporal model, and you can cut this up into chunks. There are some details to this that I won't be covering right now, but you cut it into chunks, like these chunks. And then you can use a modeling system to take a look at these chunks and try to predict the characters that the person is trying to utter. So if you had a spectrogram and maybe in the first 5 seconds, the dude is saying, I want to eat cheese or something like that, then you would take the spectrogram, you would break it up into little, maybe dozens of milliseconds, on the order of dozens of milliseconds chunks, and you would put this through a recurrent model. And it would be like, okay, the first character sounds a little bit more like I, so then we would predict I. And then there's a little bit of a space, so maybe, a pause, so we predict a space. And then it would predict W, and then it would look at the next part and it would be like, oh, it maybe sounds like an A, I want, and then it would just keep going until you get a full construction of I want to eat cheese, or something like that. So this can be accomplished using a different, variety of different methods. You can use recurrent neural networks. You can actually use convolutional neural networks because, um, at least in speech recognition, what the current letter depends on sort of only depends on the letters around them, because maybe uh, want has a dependence on the WAN because it sort of sounds like the word want. Like it's very unlikely that you would see a word like that because it's just not statistically occurring very often in the English language. So maybe you could use a convolution to analyze this. You can treat it like an image and analyze it by looking at spatially local parts of it, and you could get this whole I want to eat cheese output out. But there are a whole lot of different techniques that people are using for automatic speech recognition. They're all really cool. I won't be talking about them in huge detail because they're a little bit more complicated and out of the scope of the course. But what you should basically know is what I've written here. So first of all, we take the microphone stuff and we transform it into the frequency domain using a Fourier transform. And this makes it very much more easy for the computer to understand. And then finally, we use modeling, where we take the spectrogram, we put it through a recurrent model, and at every time step, it tries to predict maybe a word or a character that you were trying to utter. And eventually you get out this whole thing where it understands what you're saying. All right. Any questions before we dive into the lab itself? or rather just like, I'll give people a couple of seconds to send their questions in chat. But also before I move on, I want to ask if there are any questions about anything, again, even dating back to the first lecture where we talked about the fundamentals of machine learning. If you're iffy on any of the terminology or anything, definitely throw that in the chat. Or otherwise, you can just chill for a couple minutes while I pull up all of the necessary materials for the lab. Okay, so we have an interesting question in the chat. For the many-to-many, how is the data distributed again? So this is actually a good question. I didn't really talk about this in detail, so let's go back and let's examine this. So in many-to-many, and specifically, would you like to clarify which of these diagrams you're talking about, or perhaps maybe both of them? Just let me know. Is it the left one or the right one? Okay, yeah, sure thing. We can talk about both. So remember that in our neural network, right? The whole idea behind a recurrent neural network is it's really in the green stuff. The output is just task dependent. It depends on what you're trying to do. But the real meat of the recurrent neural network is formulating a way of trying to remember things from the past and recurrently updating that memory, right? So in a many-to-many situation, a many-to-many, like all of these diagrams are in the format of A to B. And when we say, either one to many, many to one, many to many, many to many, we're basically saying how many inputs do you have, right? And in the case of one to many, we talked about image captioning. You have one input, but you want to predict every single word in the sentence. That would be one to many. You have many to one, which would be, for example, you have a bunch of words in a sentence, but you just want to look at all the words and give me one answer, which is whether this sentence is toxic or not. So those are probably easy to understand. Many to many is a little bit more tricky. Like there are a variety of different applications that are many to many, but I think the most intuitive one is translation. So if you have many, many tokens in a sentence that's in English, and when you translate it to French or something, you'll still have many, many tokens. So this is a many to many problem that we can tackle. So the specific question is, for the many to many, how is the data distributed again? How is the data distributed again? Well, I can explain how it works, and then let me know if I didn't answer your question, and then maybe you can clarify what you mean by how is the data distributed. So the data here would basically look like this. You would put in a sentence. It might be, hello there, John. I don't know. So you would have this, right? So then this would be your x1, x2, x3, and you would have a hidden state, hidden 1, hidden 2, hidden 3. So you feed in hello, it knows that you're saying, you're greeting someone. You say there, it doesn't really add any information to the sentence. And then you add something there, and the neural network will be like, okay, so somebody is greeting someone named John, right? That should be what H3 says. It's going to be like a big vector of numbers, but what it should say intuitively is someone is trying to greet a dude named John, right? This is what the neural network should remember from H3. And then the next thing is that if you want to generate a sentence from this, then you should ideally take this hidden representation, which contains all the knowledge you might need about this sentence, and feed it into the neural network again. So you initialize the state with H3, and you'll be like, okay, So given H3, we already know that somebody is trying to greet a dude named John. Please, excuse me, please output some of whatever this says in French. So it might be like, I don't know. I don't even know what it would be like. So let's just say that the French would output F1, F2, and F3 or something like that. Then you would have H3, then you would put it in, and then the first thing that might come out is maybe, I don't know, maybe in French, the ordering is the same. So it'd be the French version for hello, French, and then you would have a hidden state, and then you would put the hello down here, hello, and then given hello and the hidden state that somebody is trying to create a dude named John, and also the fact that when we said hello, it already updated the hidden state to say, okay, we've already said hello, we don't need to say it again. And then perhaps French is more concise than English. I don't know, then it might just say hello, John in French. Because it's like, I already did the greeting. Now I'm going to put it into my hidden state. Let me ask, what do I need next? It'll update the hidden state to be like, okay, we've already said hello. We've already greeted them. Now the only other piece of information that we're missing is to say their name. So then it might output John after that. And then you would just keep doing this until you terminate. There's like a special token called end, where if you see the end, then you just stop terminating. You just stop generating. Does this give a little bit of a better intuition for how many-to-many works? And I guess also for the one on the right side, many-to-many is a little bit interesting, because this also, you might also argue that this is a fine representation, a fine way of doing translation, where every single word corresponds with another word. So hello corresponds to the French word for hello, hello, French, and then there would correspond to the French word for there, and then John would correspond to the French word for there. But the problem is that this isn't always the case. This is not a good model for translation, because different languages have different levels of conciseness. For example, just like the easiest scenario, hello in English is one word, but in Chinese is actually 2 characters. I'm sure we all know how to say hello in Chinese. It's 2 characters. And so if you did a many-to-many like this, it would be very difficult, right? Because then you would need to take up 2, so then maybe you need 2 different outputs from the same input, and this becomes very confusing. So this is a much more robust representation here, because again, this is sort of length independent. This is length independent. So it doesn't matter how long you require for either the English or the French translation. You can simply encode the information that someone is trying to greet a dude named John, and then given this, you can generate the French words for this. Okay, glad to know that this helped. But this was a really good question. These are the types of questions that are really helpful, not only for yourself, but I'm guessing for the entire class, because questions that you have, other people have too. Any other things before we move on to the lab? Okay, there's also a question about the homework from the API URL. So remember, a couple of days ago, we did a project where we designed a neural network, and I posted it on the internet. So it seems like it's not working. Let me just explain how to use it really quick. You just copy this thing into your browser. Let me see if it works. You would type in the first value, which is the age of the person. Let's say they're 50 years old. Second value is when they got their surgery. Let's say like 1998. Third value is the number of cancer nodes that they have, which is 100. And it should just output something. Like this one says that they won't die. Maybe because in 1998, the medical situation is so good, but maybe in the 1950s, they would die. This would give you 1 with probability of 100. So let me know if this still doesn't work for you. I will also post this in the chat. Oh, okay, yeah, the brackets are not supposed to stay there. Sorry about that. Yeah, now it should be working fine. All right. Any other questions about the contents of the class today before we get into the lab? All right, great. So let's go into the lab. Let's go to the PAC training website. Oh, it's a React app. Very cool. Okay. I'm going to send this link into the chat so that everyone can follow along. But the whole idea behind today's lab is going to be building a voice authentication app. I think this is pretty cool. When I was a kid, I thought biometric authentication was super, super cool. Or maybe, back when we didn't have fingerprint sensors, I thought that was really interesting. Also, face unlock, which you could have implemented for a previous homework, maybe, possibly. So all of these different things, I think biometric authentication is really cool. So today, that's probably what we're going to be building. Your personal audio classifier here is essentially very similar to your personal image classifier, except today we're going to be using what we learned, which were converting the input waveform into a spectrogram, and then finally using that spectrogram and putting it into a model to use it. So we're going to be doing some recordings. Now, I only have one person, like I'm the only one here right now, so I can't really test this with multiple people. So I guess I'll try to fake a voice. I'll talk in my normal voice, and then I'll try to fake a voice or something. So we can create a new label. You can follow along if you want. Then we can create a label fake Kevin. Let's see if this works. Can I record? Oh, okay, so it is working. Okay, then when you click record, I'll just say something like unlock. I hope this worked. Unlock, 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 unlock. Okay, so I have 6 examples of me saying unlock. You can see that this is the spectrogram that was created. This is the result of taking the Fourier transform of whatever signal that they got from the input waveform. And then I guess I'll also record something in my fake voice. This is gonna be weird. Unlock, 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 unlock. I don't know. It's a little bit higher, but maybe the spectrograms look too similar. I don't know. I think one way that we can overcome this is to just use a different word. So if I say a different word, um, like open, 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 open. Okay, so now you can see like I have somebody using the wrong password and somebody using the right password. If you had two different people, you should just try this with 2 different people saying the same thing so that you can figure out who is who. But then after you do this, you can click train and you can actually customize some hyperparameters. This is pretty cool. They give you some options for the learning rate. I think the default one is fine. The optimizer, this is basically the algorithm that finds the optimal weights of your model. You can either use Atom, SGD, Eta Grad, Eta Delta. Atom is usually just your go-to. And then training data fraction. Remember we talked about how your training data should be split with your testing data so that you can evaluate the performance of your model. In today's case, since I only have 6 examples, I'm just going to go with 1, which means I want to use all of my data for training. I don't really care about testing. So then, yeah, we'll be executing the code and seeing whether it trains or not. And so drop a thumbs up in the chat if you are able to get to this place and record some stuff for yourself. Okay, great. Well, it's going to take a moment to load and train right now, but then in the meantime, we can all download this file. Let me send a link. download this file and upload it into your MIT App Inventor. This will enable us to actually use the model that we created. And so just FYI, the way that you do this is you go to projects, you do import AIA from computer, and wherever you downloaded it, it should be there. I don't remember what this is called. Voice. Yeah, voice authentication diary. Click OK. Okay, so we have this thing called My Diary, and we're basically going to need to build this out. So let's see if they have any blocks here for us. Nope, they don't. Do they have any extensions for us? Yes, they do. They have the personal audio classifier. So you want to drag that in. But before I do this, I'll give people a moment to catch up. And then once you're ready, just, throw an OK in the chat. So we have a couple of people ready. I think we'll wait on the others for maybe a couple more seconds. I'd like to get a couple more people ready before we start. So, I mean, if you need more time, then feel free to take it. But I just want to make sure that everyone is trying to download things. Um, so if you still need more time, just type something in the chat to let me know. Okay. Yeah, okay, some people need more time. It's all good. For the others who are ready, just like you can treat this as a little break temporarily. Okay, it looks like this thing is taking super long to train. But we can like build out the rest of the interface before we do everything else. All right. Well, if you're still not ready, it's okay. You can probably catch up really quickly, but we should probably get started soon. So 30 more seconds and then I'll start. All right, yeah, let's get started. So um, it seems like they've given us a setup where they have screen 1 and screen 2. Okay, so we have a question here. How did you get the personal audio classifier? You go down to the bottom left, there's an extension thing, and it should have been imported when you downloaded and uploaded this file. Let me know if it isn't there, and I can send you another link. But it should be down there in the extensions, and then you can drag it to your non-visible components. All right. So it looks like the way that they set this up was that you're going to have a screen 1 where your voice is authenticated, and then there is also a screen 2 where you have a diary thing where you can save stuff. But we're going to focus on screen 1 because this is the screen where we are going to authenticate the voice. So let's just go ahead and build out, first of all, the callback for when the personal audio classifier gets a classification, because this is going to be important. Once we get a classification back from the classifier, we are going to have to do something. I think the simplest thing is to look at what the result will look like first. But to do that, we need to have the model, which apparently is broken. So I might have to redo this. Let's just train it for 10. And we'll just do, I don't know, 0.9. Maybe this makes it happier. All right. Hopefully this works. But I think there are a couple of things that we need to figure out. So first of all is, how do you classify the sound data? If you classify the sound data, you need to get a sound. Well, the first thing that we might need to do is add a button so that we can click button go. This button, click need to authenticate voice. So you have a button that will try to authenticate the voice. And then you have a, I'm not completely sure how they want us to implement the part where you do the classification. So we're going to try to figure this out. There is one thing, which is we need to be able to record our voice somehow. And perhaps we can do that using one of these methods. So let's see. The personal audio classifier itself has a model section where we can upload a model. So that makes sense. And let's see. Give me a moment while I try to figure out what's happening. Okay, so I think what we do is we go to connectivity, wait, media, layout, user interface. So it's actually called a web viewer. So the extension actually implements something called a web viewer, which it displays all of the relevant information on there. And so this actually will be the web viewer that allows us to authenticate our voice. So we actually probably don't need this button, but we'll just leave it there for now. Matthew, you don't actually need the audio classifier. Oh wait, sorry, it won't let you import the audio classifier. That's interesting. What do you mean? So is it there? And if you drag it onto here, will it just pop down? That should be what happens. But yeah, let me know if this doesn't work. Essentially what you need to do is they implement all of the features that you need on the web viewer. So you just need to go to the personal audio classifier and associate the web viewer with the diary. And for now, I'm going to delete this button because I don't think that it's necessary. So given this, let's just see what it does. We haven't uploaded a model yet, but we may be able to see what the interface looks like. So let's take a look. Uh-oh. So MIT App Inventor has crashed my phone. Let's see. We'll see whether it's necessary to use the net legacy connection. Okay. Okay, this is not great because it keeps crashing on my device. Matthew, if you mean the project, what's the error message that it gives you? It should be an AIA file, right? If it's an AIA file and you click import project from computer and you click on it, it'll definitely let you upload the project. It says server error. Yeah, this is what I'm getting. I think MIT App Inventor is generally having some issues right now. And if this doesn't work soon, then I think we'll have to figure something out. But I'm having issues getting this thing to connect, so we'll see what happens. Oh, okay, so it is working for other people. That's weird. Interesting. Okay, well, if it is working for you, great. And since it's not working for me, I will just keep going. So there's going to be a place where you can put in your model. I currently do know what the output is supposed to be because there's a document that documents basically what the personal audio classifier is supposed to give you. So we'll just use that and then we'll build out the logic. And then once this thing starts working again, we are going to we're going to do things. So, whoops. So this is the thing that we're looking for. It's going to be a list of lists where each list contains the classification and also the probabilities. And I believe that they are sorted by the biggest one, by biggest to smallest, I think. Yeah, I think this is the case. So basically, we're going to have a list here, and then we're going to need to select out the first element of the list and see if it matches our name. Remember that we defined our classes to be Kevin and fake Kevin. So we're going to need to access the first element of this array and then the first element of that array. So we need to go to our list thing and we need to index in list. Oh wait, no, this isn't the right one. We need to select list item of this list and we need to select the first index. So this gives us the result. This is the first array element, but then we need to get the name, which is actually the first list element of this list element. So then we need this. So then we have to do some logic where we compare whether or not this list item is equal to Kevin. So then we're going to do this. And then we're going to have an if statement, right? Because if this is true, then we're going to do something. Otherwise, we're going to do something else. So if it is equal to Kevin, then I will add a notifier here because this is going to be easier to implement. We'll just add a notifier. We're going to go to our notifier and say show alert or something. We're going to show the alert and we're going to say voice successfully authenticated. And then otherwise we're going to show an error that says voice authentication failed. Sad face. So in the case that the voice has been successfully authenticated, we're probably going to want to go to our our screen. And I don't quite remember how you switch screens. Let's see. So there should be another screen already created for us. It should be screen 2. Screen 2 is already created for us. Let's see. I think one way that we can just fix this is to Google this. MIT App Inventor, open another screen. Do not remember the syntax. Okay, open another screen name, and we can probably find this somewhere. Open another screen. It's right here. Nice. All right, so then your screen name would probably be screen 2 with no space. The notifier component is under user interface. It actually looks like this. It just says notifier down here. You can drag it in. It's a thing that has a warning symbol looking thing on it. So this should, in theory, be everything that we need, except for the fact that my model is not training properly and that I cannot control, I cannot connect to the companion. So let me try this one last time. And if this doesn't work, I will just leave this as further work that we can maybe do this at the beginning of the next class or something like that. Okay, so it is not working for me. That is unfortunate. But this, if anyone has actually if anyone's companion is actually working and you want to try this and you have your model uploaded, feel free to let me know if it works. I think that this should work, maybe modulo some bugs in the code, perhaps. I think it should be okay though. But yeah. Any questions as for how this works or anything regarding the project or anything before I talk about the homework? Okay, great. So again, you should probably be okay using this code. It should work. So then basically once your voice has been authenticated, it'll throw you onto the diary screen, which is really cool. And then make sure to try this out when it's actually working. It's bugging out for me. I'll try it again later and I might update you guys on what happens, but we should be good. So the homework is going to be put on the master document, but the general idea is that we'll be using automatic speech recognition once again, this time not for classification, but for text-to-speech. So you'll be building a text-to-speech model and implementing an application where you can control the functions of the application using your voice. I think in this case, it's a calculator that you can control with your voice. So it's basically a stripped down version of Siri. where you can ask it math questions or basic arithmetic, and it'll be able to answer your questions verbally, and it'll understand all of your inputs. So should be a fun project. If there are no more questions regarding recurrent neural networks or anything else, or the homework or this project, that is pretty much all I have for you today. And your